Morning. My name is Fernando, and this presentation is going to be about recent IPv6 standardization efforts. So essentially, this is like, if you are not following the work that is being done at the IETF, this is like a heads up or like a brief discussion of stuff that is going on there, right? The stuff that I try to cover here is that stuff that is related to security, obviously. There's other stuff that is going on. But if it's not related to security, I didn't include it here. And also there are documents that I cover in the presentation that I did last year on standardization efforts. And for those cases in which there have not been like much changes, I have removed that. I didn't want to rehash exactly the same thing. So presentation we did, we went through that before. What's the motivation for this work? Essentially, if you look back at what happened with TCP and IPv4, let's say 80s, 90s, essentially there were lots of things, even starting from protocol issues to implementation issues, which at some point they actually hit real networks. So there were implementations that were vulnerable to DOS attacks, networks that were subject to attacks. And only later there was work that was produced to actually mitigate those issues. You could think of many things from like traditional attacks like SIM floods, predictable sequence numbers, and many, many others. And in the case of TCP and IPv4, the TCP/IP, the traditional TCP/IP protocols, all of these issues were like found and patched after they were exploited, okay? So let's say even with SIM floods, all the SIM cache or SIM cookies and so on were mitigations that were produced once we already were subject of those attacks. Obviously, it's actually proved that it's always way more expensive to actually fix stuff after the facts. So if you actually deploy stuff that is vulnerable, and only then, only after that, you plan to produce patches, deploy those patches, and so on, it's obviously way more expensive. And obviously not just that. I mean, you are going to be exposed for a certain period of time till that gets fixed. So the idea of working on this stuff is essentially to get as much stuff fixed or improved before V6 gets widely deployed, okay? I mean, V6 has already been, has already started to be deployed, but even then, I mean, in most cases, it's not the protocol that we use every day. So in many cases, let's say the devices, the CPEs that you have at home and other boxes, either, in some cases, they might not have V6 support, or at this point in time, you might not be using it. So the idea is, to improve the state of affairs so that by the time we actually, have to rely on IPv6, things are in a better state, if you want. So I have divided the, the presentation in like two different sections. So the first section is about protocol issues, things that have to do with the protocol itself, not really with, implementations. And the second section, which is way smaller, has to do, let's say, with more operational stuff. But there's also some stuff that is mixed in between. So the first topic that I will cover is V6 addressing. We already saw yesterday that V6 addresses follow patterns. And if you were not in my presentation yesterday, it's one way or another, you must have been at one that covered the topic. So what I have in this slide is essentially, the format of a global address. So we are forgetting about the link locals and all of that, but we are just focusing on the addresses that you use for communicating with systems on the public internet. This is the global unicast addresses. The format is obviously, essentially the same as before. The global routing prefix and the subnet ID is essentially the same thing as before. Nothing has changed there. And actually, the interface ID is the same thing as the IPv4 host ID. The only difference here is that we have way more bits, okay? So these are, different techniques that you find out there to select the interface ID. I, already covered yesterday the case of the traditional Slack addresses, the ones that you have there, in which you put the MAC address in the interface ID. And for the most part, the discussion that we are going to have in the next few slides assume that you are using the first set of interface identifiers, which are the Slack identifiers, which means that the auto-configure addresses in which you essentially put the MAC address in the interface ID. So the first topic to cover are the security and privacy implications of generating addresses in that way. If you look at the first bullet, it talks about correlation of network activity over time. And the idea is pretty simple. What is correlation of network activity? Let's say that I contact some server, could be a web server, now, and then I contact the same server, let's say 5 hours from now. Well, correlating network activity is that of the server being able to tell that I'm the same guy that contacted that server 5 hours ago. The reason for which those IPv6 addresses allow for network activity correlation is, of course, because they are stable. So you use the same address now as you will use in 5 hours' time. Since the address is going to be the same, and you're going to be the only guy using it, obviously it's possible to tell you are the same person, accessing the same server. Is this the same case with IPv4 or is it different, and why? Yes, so that's one of the reasons is that since before the address space is smaller, when you do the HCP version 6, it's not unlikely that you might end up using some address that at some point in time some other node used. Okay, for some period of time it might be you might have the same address and network activity correlation might be the same. But in any case, the other reason for which, or probably the main reason for which things are different, is because you have NATs. Okay. And the thing with NATs, even with for so many reasons people don't like them, is that you can make multiple systems connect to the public internet behind a single address. So if I'm a server and I receive a connection from some specific IPv4 address, actually it could be like multiple systems because I know that the addresses are being shared. That doesn't mean that that's like a motivation for deploying NAT in IPv6, but it's actually a fact. Before, correlating network activity in that sense is like at least more difficult, if at all possible, because you are sharing the addresses. The second one is actually a little bit more nasty. Why? Because it's about correlating network activity, but across networks. Okay? So in the first case, what we had is like we had a system, let's say, connect to a server. That system connects, let's say, 8 hours later, and the server can tell that it's the same guy. Now, when we talk about correlation of network activity across networks, it means that, let's say, I connect to this network, contact some server, then let's say go back to Argentina, contact the same server, and the server can tell that I'm the same guy. Okay? Is that the case with IPv4? Oh, not at all. Why? Because when, since obviously the prefix is going to change, because since you change from one network to another, but on the other hand, since the number of bits that we use for the host ID in IPv4 is so small, I mean, obviously all of the systems are going to reuse the host ID from, let's say, 1 to 200 something, okay? So by just looking at the interface identifier or the host ID in IPv4, you cannot really tell what system is behind that address. But in IPv6, and in the traditional way in which we do stateless address auto-configuration, what you put in the interface ID is your MAC address. And the MAC address, at least when it comes to the, in theory, and at least when it comes to, real network interface cards, like the one you might have, in a hardware computer or so on, it's supposed to be a unique number. It's a universally unique number. So there's not going to be any two systems reusing the same MAC address, okay? So that's like a different way of saying that what you are embedding in the interface ID is like some serial number, your serial number. And since you are using global addresses, you are not translating the addresses at all. Whenever you communicate with any public node, essentially you are informing that system of what your serial number is. So if you look here, for example, at this first address that I have, I selected the interface ID to be 1234, the one in bold fonts, okay? So the idea is that, I connected to this network 2001 colon DBA, blah, blah, and I get this interface ID. The idea is that this interface ID will be my MAC address, so to speak. And let's say that sometime later I move to a different network, and obviously that network is going to have a different prefix, which is this one, FC00:1, but the interface ID is going to be exactly the same. Why? Well, because the MAC address is the same. So the prefix changes, but the interface ID stays the same. As a kind of side comment, which is not 100% related to this presentation, I don't know if you are aware, but the IEEE is like working on what they call MAC address randomization. So the plan that they are having is that rather than MAC addresses being stable as they currently are, at least for for Wi-Fi cards, you will have randomized MAC addresses. Apparently, I haven't read into that much, but there was a study where, let's say you are let's say like a telco that has hotspots like everywhere, and if you can see the MAC addresses of the system that are polling the network to see if there are any Wi-Fi systems around, any Wi-Fi networks around, they can actually see that you are nearby the hotspots, and if they have control of all the hotspots and they can look at your MAC address, essentially they are able to track you, okay? So that's even like at a lower layer than IPv6. So the IEEE is working on that already. From my perspective, I'm not sure where that is going to go to, because there are in many different, so the infrastructure or some systems that we have right now, to some extent, they rely on the MAC addresses being stable, okay? Even with some simple systems that they want, like the captive portals that you use to access the internet, they look at your MAC address to be able to identify whether you are a party that is supposed to access the network or not. Now, if we start randomizing the addresses, then that could mean that if you go out of range of the of the hotspot and then connect back, you have to re-logging, for example. And from the point of view of the system enforcing controls, you look like two different systems because you have a different MAC address. So you look like you are a different system. So even when they have made some testing around that, I think that deploying the randomized MAC addresses, I don't know how easy that will be. In some cases, you go to a cafe or something in my work, but when it comes to systems that are supposed to connect to some organizations, Wi-Fi network and so on, I don't think it's going to be that simple. So the point here again, when it comes to network activity correlation, is that the interface ID is stable when you move from one network to another. That's one part of the problem. The other part of the problem is that it's a number that is unique, okay? So it's universally unique. It's not going to change as you move from one place to another. The third item here is that of network reconnaissance. If you were yesterday at my presentation, the idea was very simple. If you look at IPv6 addresses, they follow patterns. And even when many people have argued for years that scanning IPv6 networks is like impossible, truth is that when you look at the patterns that address follow, an attacker can just target that single pattern and then discover the systems that are connected to that network. Here is just maybe one of the most trivial examples, the addresses that we call low byte, in which you have the interface ID set to all zeros, and then you just change the last byte. So let's say the first system has this address, the second system has this other address, and so on. Obviously, if you wanted to scan that network, you're not going to try random addresses, but you do it in the same way that you do for before. And the final one, you could say it's more of, security and privacy. The other issue is that since you embed your MAC address in the interface ID, essentially, your MAC address becomes visible to any node in the public network, okay? So let's say I could, connect to this network 2001 DB8, and, this is the interface ID that I configure. This interface ID contains my MAC address, and obviously the MAC address has an IEEE OUI that identifies the vendor and, 3 other bytes for selecting the system. So if you look at the upper 3 bytes, these ones, they identify the vendor, which means that, for example, just by looking at the address, you know what kind of device is behind that address. So it's easy to, easier to target. Let's say if you have a device-specific attack, you don't even need to fingerprint the system or anything because, well, the fingerprint is already in the interface ID, okay? So you are disclosing more information than you should. The bottom line here, and I can, give you the file name later, is that when you look at, virtually every single protocol that the IETF has produced that contains some sort of identifier. I mean, in this case, they are interface identifiers, but then you have the same, you have like, transport protocol port numbers, you have, IPv4 and IPv6 fragment ID numbers, you have DNS transaction IDs. There are so many different kinds of ID, TCP sequence numbers too. What you usually find is that, the IETF has done like a rather poor job about that. So in this particular case, if you think about interface identifiers, the only thing or the only requirement that we really have on the identifier is that it is unique within that network, okay? So if I connect to this network, I have to configure an address. The number that I put here must be unique within that network. But nobody said that, I have to put, the information about my MAC address there, or that the interface identifiers have to follow, some pattern, or even that if I move from this network to another, I have to use exactly the same identifier. I mean, there's no requirement for that. I mean, it's just done that way, but it doesn't need to be that way. And usually, the more that you overload any kind of identifier, well, usually the more into trouble you get when it comes to security and privacy. So what's the work that we have done in this area? So very recently, I think it was last week, we published 2 RFCs on this topic. The first one, 7721, is about the security and privacy implications of IPv6 addresses. So essentially, it's an RFC that covers, everything that I had in this previous slide, but with more detail. The second one, 7707, is the one on network reconnaissance, which essentially covers like all or most of the stuff that I covered yesterday in my presentation. This is stuff that has just been published. But, this work essentially is about, talking about the problems, like how these problems can be exploited and, why we actually have a problem. But no one of these 2 documents does anything to actually, solve these issues. Let's see what we have, what we have done and what we are doing to mitigate these issues. So years ago, this could be something like 10 years, there started to be discussion about, the V6 addresses leaking out information about the user, okay? So the IETF came up with this idea. They are usually called privacy addresses, but I think a better name is temporary addresses. They are addresses that essentially they change over time and they change to a different random number. So the idea is simple. You connect to a network, you get a random address. Sometime later, doesn't matter. It's the implementation specific. That number will change to a different number. So you have an address that is changing all the time from one value to another, okay? The idea with these temporary addresses is that they don't replace the traditional addresses, but actually they are used along them. So you have the traditional Slack addresses that include the MAC address, and in addition to that, you configure the temporary addresses. Why? Well, because even when the temporary addresses might be great from a security and privacy point of view for outgoing connections, like for example contacting a server, when it comes to receiving incoming connections, they are not that great because they are changing all the time. So that could mean that, for example, let's say just to give you an example, let's say that you are a web server, okay? You wouldn't really have like an address that is changing all the time, because that would mean that, well, first of all, you have to be updating the DNS every time that the address changes, and so on. So if you want to receive incoming connections, you want the addresses to be stable, not to be changing all the time. And since, in principle, you don't know beforehand what some system is going to be used for. I mean, you install a Linux system and it's impossible to tell whether that's going to be a web server or my workstation. Well, by default, every single implementation, if they employ temporary addresses, they do it along with the traditional addresses, okay? So we keep what we have, but in addition, we use the temporary addresses. And for what purpose is each of these addresses employed? Well, in theory, at least, you employ the temporary addresses whenever you want to do an outgoing connection. And typically, when it comes to incoming connections, you just receive connections on any address. But obviously, if you are a server, the address that you would publish on the DNS would be the stable address, the traditional Slack address. There are a couple of things to note here. So the first one has to, well, there are two aspects. Let's say there's the aspect of scanning, and there is the aspect of tracking too. When it comes to scanning, do these addresses mitigate scanning attacks? Yes or no, and why? Why? Exactly. So that's the point. As long as you have an address that can be predicted by an attacker, it doesn't matter if you have like 100 other addresses. Obviously, if I'm an attacker, the address that I'm going to try to find is the one that is predictable. If you also have 10 other random addresses, I don't care. As long as I can find one, that's enough. So that's one thing. The other thing has to do with tracking, okay? Like, correlating network activity across networks. So in principle, let's say if you're employing temporary addresses, and let's say I'm a web server, and I want to do like, passive tracking, I mean, without sending any proof packets, just listening to, the packets that you send me, you could argue that temporary addresses, they do mitigate network activity, network tracking. Why? Because if you connect to my server from this network, you're going to use some random interface ID, then you connect from some other network and you use a different ID, okay? Now, the problem is that if I wanted, I could still track you, and in what way? Let's say that, let's go back to this slide that had two addresses here. So let's just say that I know that he could be in two different places, like at Troopers and at his house, okay? And I know that at Troopers, they use the prefix that you have over there, the 2001 DB8. And I know that at his house, he's using FC00:1. So if I want to check whether he's at Troopers or at home, I just ping this address and this other address, okay? So I can prove the address that I know he would have at home and the address that I know he would have at Troopers if he was there. Why? Because if the interface ID is always constant, you always use the same interface ID, I know that whatever network that you connect to, your interface ID is going to be the same. So I can predict the address that you would use there. Obviously, in that case, you have to do active tracking. So I had to send the packet to a network to see if you are there. Where in the other case, well, I had to, I could just track you by listening to the packets that you send me. So the bottom line here is that the temporary addresses, they mitigate to some extent, all of those privacy attacks that are passive, like you just try to track a system without sending any proof packets. But if the attacker is able to prove different networks, these privacy or temporary addresses, they don't mitigate much. Obviously, one of the biggest problems here is that when the temporary addresses were, let's say, standardized and implemented, we didn't do anything about the other actual addresses that were, the ones that were not nice at all, the ones that embed the MAC address. So we, standardized something else, but we still kept those addresses that are not nice from a security and privacy point of view. So not that long ago, if you thought about what kind of addresses we had predictable and stable addresses. Those are the traditional SLAC addresses in which you embed the MAC address. We don't have predictable and temporary. That would be like, doesn't make any sense at all, okay? We have temporary and unpredictable, which are the privacy addresses.
We have such devices, unfortunately.
Sorry?
There are cheap devices out there. I have one from a big customer.
Uh-huh.
And manufacturing devices. That's create or to make a drive cheaper.
Uh-huh.
Avoiding license the OE from the IEEE Institute.
Uh-huh.
You get basically something that is semi kind of temporary. Now you switch off and switch on the stuff. Otherwise it starts with a new random MAC.
Okay, okay.
It's really crazy.
Well, what I knew, it wasn't that case, but there was a guy, H.D. Moore, like this. He published years ago, I don't recall, in some conference in the US, like a study of MAC addresses. I don't recall the details of how he obtained those addresses, but what the guy had found was that MAC addresses were actually reused. It was like, if you had vendor X, and they were not even like, setting the addresses randomly. It was like, well, okay, whatever. I'm not going to, apply for more addresses. So they will ship the same, different devices with the same MAC address. Uh-huh. I don't know what, I don't know if they intentionally, maybe they sold, let's say you have devices with the same MAC addresses, so let's say we send these to Europe, these to, the Americas, or they didn't care and they shipped the same devices, and, if you were unlucky to have two devices with the same MAC address in the same network, well, your problem.
This is one also using after certain product lifetime. When the product lifetime is known, the other one is basically kind of an unknown when the device gets replaced and you get the replacement back.
Uh-huh.
So all kind of
Uh-huh.
only depends on what kind of device.
Uh-huh. Okay, so we have temporary and unpredictable addresses, which are the RFC 4941, which are the privacy or temporary addresses. And last year, we standardized this scheme, 7217, which is like a middle ground between the two. So they are addresses that are unpredictable. They are stable within a network, but they change when you move from one network to another, okay? Those addresses are meant to replace not the temporary addresses, but actually the traditional SLAC addresses. And this is the algorithm that we use, like a simplified version of the algorithm that we use to generate these addresses. In principle, to make things like easier to understand, just assume that so we have that function f over there, and for a second, let's just assume that the only two parameters are the prefix and a secret key, okay? So for the time being, forget about, these three parameters that you have in the middle, the network interface, network ID, and counter. Now, if you have what's supposed to be a cryptographically secure hash function, okay, and you include, or you include as a parameter a prefix and a secret key, every time the prefix changes, obviously the result of the hash function is going to change, okay? The secret key, the last parameter here, it's supposed to be, obviously not known by the attacker. I'm not going to say whom, but years ago we published a different specification which was using the same kind of algorithm but for a different thing. And we got an email from a very big vendor, and they were asking if the key really had to be, secure. It was, well, the whole point of this is that you don't disclose the key. If you're going to implement this and the key is going to be known to everyone, you are wasting your time. So obviously, the whole scheme depends on the key being, unpredictable. Now, let's assume, I think that I have an example after this. I don't know. Let's assume that you move from, let's say, one network here where the prefix, let's just say, is A, and you have this other network where prefix is B. When you connect to this first network, the input that you're going to give to the hash function is going to be this prefix A plus, obviously, the secret key. And you will get some output as a result of the hash function. That's going to be your interface ID. Now, let's say that you move to this second network in here. The secret key, obviously, is the same, but now the prefix has changed. As a result, the result of the hash function is going to change too. So let's say that here you got the address 12AB, and here you got the address ABF, whatever. Let's just say that you were in this network and now you go and move back to the original network, the one in which that you were in the first place. Since the prefix is going to be the same as before, and the secret key is going to be the same as before, you're going to get the same address, okay? So as long as you stay in the same network, you get the same address. That address is going to be unique in that network, and the interface ID is going to be unpredictable because we are using a function that is supposed to be cryptographically secure. You move to a different network, you get a different interface identifier. As long as you stay in that network, or you go elsewhere and you connect back to the same network, you get the same interface ID. So from the point of view of this network, or from each network, your address is stable. So while you are connected to that network, you always keep the same address. But when you move from one network to another, your address changes. So the benefits of this scheme is obviously that, let's say from an operational point of view, let's say that you have ACLs or other kind of stuff implemented in the network, then you can rely on those addresses being stable. Okay? Even it's easy to, correlate the activity of your users. If you know that, the system with this address, was infected at some point in time, you know what system that was, okay? But what you win with this scheme is that, well, first of all, the addresses are unpredictable, which means that, you couldn't scan these addresses, or actually, well, you could, but it would be like a /64, which means that it would take forever. It's better to try something else. And the other thing is that, it's not possible to track the systems as they move from one network to another because the interface ID changes. If I'm in this network, this is what my ID looks like. I move to a different one, and my ID changed. So there's no way to correlate the two. We published this one 2014. I thought it was last year. Well, let's say 2014. And what's the implementation status of this? Well, Linux has already implemented this as a replacement of traditional Slack addresses. They did an implementation in the kernel, in Network Manager, and there's also this, I think I used this stuff with the Raspberries. And I think FreeBSD uses this DHCP package too. So they are essentially three different implementations. Obviously, the Network Manager is like a user-level implementation, whereas the first one is in the kernel. Sorry?
I missed it because Windows is using this. I'm not sure Windows 7 not, but at least 8 or on 8.1 you have a very similar behavior.
Not exactly. I mean, Windows did something that is better than what the IETF did, but still not good enough. So what they do is, rather than embedding the MAC address, they embed a constant random number. So it's a number that, let's say, it's those addresses mitigate address scanning because within the network the addresses don't follow any pattern. But when you move from one network to another, you keep the same identifier.
Okay.
So they allow tracking, for example. So it's not good enough. I mean, still better than what the IETF did, but still not good enough. I don't know much about how the process of packing the distros and so on use. But as far as I talked with some of the guys that did the implementation, they told me that the newer distros of Fedora and I think Debian too this year should ship with this on by default. which is a good, a good thing from a security privacy point of view, and it's also like a heads up that if you are relying on the traditional Slack addresses and you upgrade the operating system, all out of the sudden they will change, okay? Because right now you have the ones that are based on the MAC address, and once this is deployed, they will change to something that looks like random. Let's put things this way. With Microsoft, things, how should I say it? They were changing over time. So initially, when I published the internet draft version of this RFC, they were like yes or no, yes or no. And nowadays, they are kind of like at least in favor of replacing the traditional Slack addresses. So far, they seem to be supporting replacing those addresses with this. And actually, with this document in particular, I was extremely careful to publish it in a way so that the document wouldn't get patents on it. Because the problem is that, if you get patents on this, well, in practice, it becomes hard to implement, at least, on the systems that I use. And actually, at some point in time, there was a suggestion by people from Microsoft that, well, this might be affected by one of our patents. But I fought that one, and they, quit, assuming that they might, apply a patent to this. From my perspective, I mean, it doesn't make any sense. But, nowadays, people like patent any crap, so anything could be patented. It's insane. I have read through some patents about protocol stuff, and I cannot even believe that the patents are accepted. And as far as I know, it even costs a lot of money. So it's like a game for big companies. It's that you have any crap and you have like a team of lawyers, and they have the money to apply for it. But on the other hand, the guy that is let's say working on an open source implementation or the like, I mean, he's fucked. If there's a patent on something, there's not much that they can do. Sorry? That depends on where you implement this. For example, for the network manager implementation, it's a user space implementation. So you don't need to store it in the kernel. Actually, it doesn't make any sense to do that. But if you do a kernel implementation, well, probably you are going to implement it there.
But you can't roll it out like different PCs.
Sorry? No. No, what we suggest, and that's what we expect, distros to do, is that whenever you install the system, the key is generated and set to a random number. And then what we say in the spec is that the implementation should allow you to manually set the key. And why? Because let's say that for some reason you want to destroy this box that you have, and you want to reinstall the operating in a different system, but you want it to have the same addresses. Well, you have to set the same key. So what we say is that there should be a way for the administrator to take a look at the key and to be able to set the key. Okay? Exactly. Yes. If not, the problem is that you're going to have two systems with the same address. But well, I guess with the virtual machines, they can get away but randomizing the MAC address. But yeah, in this case, you should be able to change the key. If not, you get the same address in the two systems. Yeah.
What about these new identification mechanisms with installations where you need stable addresses both and so on? Maybe something like IoT. For IoT, you don't need privacy. You might try to mitigate different things. But on the other hand, you need to be sure that however whichever way you have the startup sequence, the individual device always get the same stable address.
Well, in this case, when you install the device, from that point, you know,
But if your switch has a DAD involved, and if a DAD has
well,
a hit instead of a miss, you will rerun.
yes, but in that respect, you could, you know, argue that, for example, if you have two devices that have the same MAC address, they might get the same address and you have a conflict too.
Yeah, for cheap device, yes.
Our take on this is that, you know, so when I showed you the, you know, the expression, that the algorithm that we use, there's like this variable counter here. Okay, so the idea is obviously that when you generate the random interface identifier, if there was, you know, like a collision, there were two systems using, you know, the same ID, what you do is you increment the counter and you know, redo the computation. Now, from my perspective, we included that for, let's say, for completeness sake, but the subnet size is 64 bits. 64 bits. So if you do the math, you'd have to have like an extremely large number of systems or be extremely unlucky. If you ask me, well, could it be the case that, yes, I mean, in theory, yes. But, you know, the chances, I think that they are very small. So it's 64 bits.
Yeah, I know, but the problem is we don't have, if you combine different methods, we don't have the distribution. So
Yeah, but to some extent,
gets worse.
but to some
I don't know how much.
But to some extent, you know, you already have the problem because, for example, you have the privacy addresses, you have the traditional Slack addresses, and you have the scheme that is employed by Microsoft.
Yeah. It's not against.
I mean, if you,
URC is just about asking a problem that is going to appear if I mix all these different systems on a newer system. Basically, coexist because they assume that might be actually some detection. It doesn't matter because I rerun. And it's used in the situation that
well, there are two different, let's say, workarounds for that. So the first one, which is actually mentioned in the, you know, in the specification, is not that we say, well, you have to do it that way, but the spec says that if you want, what you could do is record the value that you use for counter for the specific prefix. I mean, obviously that requires additional state, because in theory, I mean, if you connect to so many different networks, then you have to record one counter value for each prefix.
I'm rather thinking just around the IoT.
But you could think of an implementation that say that has room for storing the counter for 4 different prefixes, and that's it. And then, that's one of the things. The other thing is that in order for you to get a different address, so let's say that I have this system that is A and this system that is B, okay? And let's say that this one has let's say that this one gets the address number 1, and this one, which I bootstrap later, gets again the number 1. So when I rerun the algorithm, let's say I get the number 10, okay? As long as these two systems get bootstrapped in the same order, well, they are still going to get the same. So you have to be unlucky, extremely unlucky. But even then, what we say in the spec is that, you know, it's one of the possibilities is that you record which counter value you employ for which prefix. So if you are really concerned about that, that's what you do. Okay? Okay. Yes.
I'm assuming the secret key size is the same size as the hash function.
I don't. I'm thinking about what we were using for the key and the hash. I think that for the hash function we were recommending SHA-256, and for the key, I think that we said something like at least 128 bits, I think.
Basically, the key is actually what's defining your random.
Yeah,
Is really random.
Yeah. The security of the whole system depends on the secret key. Yeah. Yes. And also, that's also why we think that the best way to go is for the, let's say, the operating system installer to select a random number when you install it, as opposed to asking the administrator to set a password. Because if they are going to, set a 5-digit word for it, it doesn't make any sense. In any case, let's say that this is mostly for obfuscation. Okay, so it's not that it's like a digital signature of something that it's like you extremely need it to be safe. I think that, within the limits that we are talking about, you wouldn't bother trying to, to crack this. So you might remember that in V6 there are two different ways of auto-configuring systems: Slack and DHCP version 6. Okay, so this just applies to Slack, not to DHCP version 6. Now, with DHCP, the thing is that there were quite a few implementations that would list addresses that were sequential. Okay, so rather than listing random addresses, they would produce addresses that were sequential. So what we did was to, let's say, propose or specify like a DHCP version 6 port of the same algorithm. In this case, obviously, it's the DHCP server that runs the algorithm, not the client. Okay. So the idea is extremely, similar, with the only difference that, for example, here for the expression, you have the client DUID, which is like a unique identifier for the client. That's something that you include in the hash function so that, each client gets a different address. This document was originally adopted by the relevant working group at the IETF. It was, how to say it, this adopted later, and from my perspective, without any reason at all. Politics, I would say. Of the people that argued against this document, there was people that are actually in favor of Slack rather than the DHCP. So my take is that they didn't want to improve the DHCP because it was kind of like their competitor, okay? And eventually the working group dropped this. So now we are going to publish it not as a formal specification, but as an informational document, which means that it's not the, let's say, full standard, so to speak. This one is it's supposed to be in the, it's being processed by the RFC editor. So it's kind of like in the final stage. As far as I was told, they are now, asking the IETF if there is like any conflict with this document, and if everything goes by, it should go forward. Well, this is the same thing. Yes.
Short question.
Yeah.
Would this have to be normal IA versus stable addresses or to temporary addresses?
This is supposed to be applied to the stable addresses. Yes.
The traditional pool.
Exactly. Yeah. So the idea is, because you have quite a few implementations that would select or list the addresses in the same way as before, as sequential addresses. So the idea of this is so that each system gets a unique address, but that is not predictable. And one benefit of this algorithm is that you don't really need to maintain state at the DHCP server. Why? Because it's the algorithm that always gets you the same ID for the same client. If you want the addresses to be stable, but you don't employ something like this, then you have to have a database, like a list database, in which you say, okay, I list this address to this client, so that when the same client asks you for another address, for a new address, like a few days later, you list the same address to the same client, okay? You have to remember which address you list to which client. But in this case, it's like the algorithm that remembers the address. As a result of applying this function, you always get the same result. Procedural caveats, or this is another way of saying political issues around this. So years ago, I published one document that essentially discussed the security and privacy implications of V6 addressing, proposed a scheme to replace the traditional scheme. That was it. Well, the IETF exploded that into 3 different documents. So one document for specifying the mechanism, one other document for discussing the security and privacy implications, and then one other document that tells you, well, you have to do what this document says, okay? So strictly speaking, the situation right now is that you have 7217, which specifies a scheme for mitigating these problems, but nobody tells you that you have to implement it. And this document, the one that says default IIDs, it's still in the works. From my perspective, it has been stalled and delayed unnecessarily. That's as much as I can say. That's as much as I can say. So how many minutes do we have left? Okay, we're fine. Yeah, and there was even like funny discussions. The first time, when I published the first version of this, I even was approached, I'm not going to mention guys or companies, but I was approached by a guy from a mobile phone company saying, why do clients need to have privacy? Or why, this was like the pre-Snowden thing. So nowadays I think they wouldn't say it, even if they thought it. But, and this guy was arguing that should be like an opt-in. Right? So if you really wanted this, you had to configure that, which obviously doesn't make any sense at all. The typical user, you have to give the user like a good default option. And then there was, at the same time frame, let's say I was suggested that if I wanted this to move forward, I had to incorporate as authors some people from some large companies. So it was like, it was a lot of luck and lots of energy and effort to get this published as it is. At times, things in the IETF can be like hard. Extension headers. So theory, this is what has been covered so many times. This is the structure of an IPv6 packet with the extension headers, in between. This is the way fragmentation is performed in IPv6. So rather than having the necessary support, in the base header, if you want to fragment a packet, you need to add a fragment header so that you can, put the 2 chunks of the packet into different packets. So at the time, years ago, there was discussion in IETF circles that operators were dropping IPv6 fragments, okay? But there wasn't any data about that. It's like, when lots of people talk about something that nobody saw and nobody had concrete data, but everyone is saying it, so it must be true. So that was the case. So I decided at the time to, measure this and to see to what extent, these packets with these IPv6 fragments were being dropped. And since I had to, work on the tools, I said, well, let's not just do it for IPv6 fragments, for the rest of or some of the other extension headers. So we ended up publishing this document that right now you should replace the because it's a working group document, okay? And essentially what this document does, it, first of all, it provides the data that we got from measuring the support of extension headers in the public internet, but we also give like instructions step by step on how you can reproduce the results that we got. So the idea is that, let's say, if you look at the results and you say, oh, well, I don't know if that's true, well, we give you, like a very specific or very concrete advice on how you can reproduce the results by yourself. These are the results that we got. If you were in my presentation yesterday, it's the same thing. Packet drop rate, which essentially means that for different extension headers, it's between 10 and 40% of packet drops. This is the percentage of cases in which, when you see a packet that is dropped, what's the percentage of cases in which the packets are dropped not by the final network, but by an intermediate network, okay? So put things in a different way, what this slide is trying to summarize is when you see that a packet is being dropped, in how many of those cases, or what's the percentage of cases in which the packets are not dropped by the destination IS, but actually by somewhere in between. Obviously, the more in the middle in the network that the packets get dropped, the worse it is to some extent. Let's say that I want to use extension headers to communicate with him. If it was him, the one filtering the packets, and he's the guy that is actually interested in using them, well, he'll do whatever it takes, to actually remove the filters. But if the packets are being filtered by some intermediate network, well, to some extent, you don't have much of a control of that, okay? So these are the results that we got for two different data sets. Again, the results are like horrible, and actually, I don't know if I had it in, but the funny story with this is that when I started doing the measurements, the results were so bad that I actually spent a lot of time working on the tools because I assumed that there was a bug in the tools, that the results couldn't be that bad, but they are that bad. This document was like controversial at the IETF, very controversial. Why? Because you are essentially telling the IETF that this base feature of the protocol doesn't actually work. So if you actually try to use extension headers in the public internet, you have very small chances that your packets will get to the intended destination. But eventually, this document got adopted, and it's like in the final stage of the publication process. So it would seem that it's going to move forward and be published. So we published this document, and when people couldn't actually argue that the situation in the real world was different, then they started arguing, well, but yeah, okay, the packets are dropped, but maybe it's because of implementation bugs. It's not that people want to drop them. It's like there could be implementation bugs or configuration problems. So they were arguing that the drops were not intentional. So what we did is we ended up authoring this other document, which essentially discusses the reasons for which, if you are an operator, you may want to drop these packets. It's not an argument in favor of dropping them. It doesn't say you should drop them, but it actually says, look, it's not that dropping these packets is bad. Actually, there are reasons for doing that. You might share these reasons or not, but these are the reasons for doing so. In this document, we cover both security and privacy implications. We summarize them, actually, with pointers of work that has been done in this area. When it comes to the security implications, well, at this point in time, they should be known by everyone. Evasion of security controls. Obviously, the packets look like a mess. So if you are like a middle box that want to perform the packet inspection, it's very difficult with extension headers. Second one is that there are many implementations that if they have to process the extension header chain, they have to process the packets in software, okay? So all out of the sudden, thanks to the extension headers, you switch from, processing the packets in hardware, let's say pretty fast, to processing the packets in software. And obviously that makes for a DOS vector. The third one has to do with implementation errors. And the idea is simple. Apparently everyone got the implementation of extension headers wrong one way or another. If you look at issues that have affected IPv6 implementations, many of them have to do with extension headers. Like if the extension header is too long or has like incorrect value or whatever, the system crashes or stuff like that. And the final one are issues that are related with specific extension headers. As an example, let's say, obviously, if you look, let's say, at the fragment header, there are, security implications associated with that header itself. So the other ones are like generic for any extension header. What about the operational implications? So the idea is that in many cases, you need middle boxes to obtain layer 4 information. And why? Let's assume, for example, that you have a router and you want to do load sharing on that router, okay? Typically what you do is you try to send on the same, you try to send packets that belong to the same connection, for example, same TCP connection over the same link. Why? In order to prevent packet reordering, okay? So nowadays, the way in which we do that is, well, the middle box looks not only at the IPv4 packet, but also looks at the transport protocol header. And it finds, for example, the transport ports. So if you look at the IP addresses, the transport ports, you can identify the different, for example, TCP connections. The problem with V6 is that since the extension header chain can have any arbitrary length, then it can become very hard, if at all possible, to actually spot the layer 4 information. There are even implementations that, when they have to forward or process a packet, what they do is they receive a packet on one interface, they copy a limited set of bits from the beginning of the packet, let's say 60 bytes from the beginning of the packet, and do all of their processing on those 60 bytes, okay? If the information that they need is not there, well, they have the option of dropping the packet or sending the packet to the CPU for, processing the packet in software. So obviously, as a result of that, if you drop the packet right away, well, that's where you get the packet drops. But on the other hand, if you send the packet to, for CPU processing, for software processing, obviously that's a vector for DOS. I mean, if the attacker knows that you do that, he could just send a very long stream of packets with extension headers, and that would obviously overload the CPU of your device. So while we were discussing this, there was people that were saying, well, but why do you have to look at the layer 4 information if it's a middle box? It's a layer 3 device. So we say, well, among other things, for load sharing. And you know that in V6, there's this field called flow level. Flow level is a field that for about 15 years, nobody knew what it was for. And eventually we had like 20 bits there, and it was like, well, let's use it for something. Enough, okay? So we got the final specification on what to use the flow level for, like maybe 4 years ago. So it's not really widely deployed. The idea with the flow level is very simple. You put some random number in there that is supposed to identify a transport protocol instance. So if you want to identify a TCP connection, you wouldn't really need to look at the addresses and port numbers, but just look at the IP addresses and the flow level. What's the problem with this? Nobody sets this, at least for deployed systems. So yeah, in theory, you could use it, but in practice, you can't. Now, there is another reason for looking at layer 4 information, which is, for example, enforcing layer 4 ACLs. So if you are an operator, it could be the case that you want to, protect your own infrastructure or even protect the infrastructure of your client. And in that case, you need to apply layer 4 ACLs. So you actually need to get to that information. The idea of sometimes they, have this, let's say, puristic or unrealistic view that if it's a layer 3 device, it doesn't look, inside the packet. Well, that hasn't been the case for so many years. I mean, in theory, that could be the case, but it doesn't happen in practice. So there are multiple reasons for which you may have to look at or you may need the layer 4 information. If you need that information, well, the extension headers are extremely painful. Usually the options are that if you find them, well, you drop the packets. This document is being discussed right now at the V6 Ops working group. And from my personal perspective, the people that are, let's say, more of V6 purists, obviously they don't like the document. Again, this is like a way of saying this protocol that you specified is not really deployable. And people don't like to hear that. Huh?
Your key is actually.
Yeah. Yeah. So still being discussed. Well, we discussed this too. The other reason, but for me this is not the real reason for which these packets are being dropped, but this is for completeness sake. If you look at, different implementations, there could be cases in which, for example, you have some specific extension header, but there are subtypes of that header, like routing header type 0 versus routing header type 2. And there are implementations that do not provide the right granularity level. So if you want to filter routing header type 0, well, you have to filter all types of routing headers. But again, we included this for completeness sake, but for me the real reason for which these packets get dropped is because they make it painful for any middle box to actually find the layer 4 information. Fragment header, this is the syntax of the fragment header. It is essentially the same. It's like putting all the before fragmentation fields in a separate extension header. That's it. Seen before, you have a fragment offset that essentially tells you, where in the piece of the puzzle of the packet this piece falls. And you have an identification field that is employed to identify fragments of the same packet. Okay? So if they have the same address, the same source and destination address, and the packet has the same identification field, it's supposed to be fragments of the same packet. Well, the security implications of fragmentation in general are known, but in particular, we were looking at, whether the fragment ID values were predictable or not. But at the time we started, looking at this, it was like, well, this is the same crap as in IPv4. It was done in the wrong way in IPv4. It was fixed in IPv4, so you would assume that you wouldn't have the problem in V6. And when we actually look at implementations, it's the same thing. And there are other systems, for example, Cisco, predictable fragment ID to global counter. Okay? This is stuff that it's like hard to understand. It's like for the last 20 years, everyone knew that if you had to put an identifier, it shouldn't be predictable. But every time there's a different protocol, we always go the same path. Like using global counters, some people find that they are, trivial to exploit. Few years later, they get patched, and then some other protocol is produced, and we repeat the same story over and over again. Yeah, so we have Cisco in there. There were some systems like Solaris and Linux that when we notified them of the problem at the time, they produced it like patches right away. At least in that sense, it was good. And then there was Microsoft, which was like a waste of time. The guy, some guys, explained to me that they have like different layers of, if you contact security at Microsoft, they have like different layers. And apparently the layer that has a clue is like layer number 40, which you never get to. In my case, I stopped reporting stuff to them. And I think, well, Mark Oise, it says the same thing. It's like you spend a lot of time and, it's for their benefit, so. Sorry? No, this is, I did, yeah. And there's, if you look at the toolkit, there's a tool called Frag6, oops. I think there's an option, something like frag ID or frag ID policy, in which you specify a target address, and the tool itself tries to figure out the algorithm that is being employed for generating the IDs. Obviously, we just detect global counters, per destination counters, and a few others, not every possible algorithm. Okay, so we publish this document, RFC 7739, which essentially discusses the problems of predictable fragment identifiers. It proposes possible algorithms that could be employed to set the fragment ID. Obviously, there are a number of trade-offs here, like performance, how predictable or not the frag IDs can get, and so on and so on. And the problem was that at the time when we published 7739, that document was a formal update to the IPv6 specification. Now, what's the problem with that? Many people at the IETF want to pretend that the protocol has been stable for so many years. So rather than accepting the fact that that's not the case, they actually try to stop every possible update to the protocol. Okay? So this is kind of like a behind-the-scenes update, because the RFC that we publish doesn't really update RFC 2460, okay? And if you look at this other document, which is the revision of 2460, it silently removes the algorithm that was recommending predictable values. There was one specific case. How much? Minutes, okay. There was one specific case that has to do with atomic fragments, or what we call atomic fragments. I will not discuss all of the details because we'll get sidetracked and need to take a long time. But the idea is pretty simple. If you look at the core IPv6 specification, it says that if you receive an ICMP message that claims an MTU smaller than 1280, you have to send any further or any subsequent packets with an extension, with a fragment header. Okay? So let's say I'm sending traffic to him. I receive one of those ICMP error messages. So right after that, I have to include a fragment header in all of my packets. The reason for which we call these atomic fragments is that it's not really an actually fragmented packet. The whole packet is here. The only thing that we did was to incorporate a fragment header. This is employed for translators, but we are not going to get into those details. But the question here is, can we actually use these atomic fragments for attacks? Well, the idea that I came up with was this one. If you remember the numbers that I showed for the support of extension headers in the public internet, you may recall that packets with extension headers were dropped from a 10 to a 40% of something. So to put things in a different way, if he's sending packets to him and somehow I can cause him to start using extension headers, then it will be the network itself the one dropping the packets. So it's not that I drop the packets myself. Actually, I cause him to start employing something that will eventually lead to packet drops. So the scenario will be something like this. Let's say there's this server sending information to the client, and there's an attacker somewhere. But what he does is simply spoof a single ICMP packet to big message to the server. Once the server receives that packet, it will start sending any subsequent packets with a fragment header. But if the network is dropping packets with extension headers, then all of these packets will get black hole, okay? So essentially, it's trivial to cause a denial of service attack just by sending one single packet that triggers the use of fragmentation. Then it's the network itself, the one that drops the packet. So this is a test that I did it's like a very simple way to try this. At the time I tested this with the kernel.org and against my own connection. So what I did is, this is the IPv6 address of, or at least at the time, www.kernel.org. So I do a telnet to port 80 just to test that everything was working fine. Then what I did as a second step here was to send a spoofed ICMP packet to big error message. I mean, this is just setting an MTU, for example, here to a value smaller than 1280, and these are the IP addresses of my system and so on. And then what I did was to test V6 connectivity again. And in this case, what you get is a timeout. How long the timeout lasts, or how long does the attack last? For about 10 minutes. So with a single packet, you get 10 minutes of denial of service. Okay? Again, so what we are relying on for the DOS is that it's the network itself the one dropping the packets. So our attack consists in triggering fragmentation at the vulnerable system. And we rely on the network dropping the packets.
You're only targeting the client for which you need to know the address?
Let's see. At least in theory, yes.
And also rely on not having filtering, right?
Not. Why? No, because when you have an ICMP message, so let's say this is the ICMP message, this is the header, okay? Oh, well, this is the IPv6 header of the error message. Here, the source address is the source address of the router that found the problem. So I can use my real address pretending that I'm some sort of router in between. The only address that you have to spoof is that in the payload of the error message, you include a piece of the original packet. But nobody looks inside this. So you don't really need to spoof the address. So even if there's like ingress-egress filtering, it's not going to help. And there are other scenarios. I mean, you were talking about the client. So you could say, well, maybe with the client, you might not know the address. But let's say that you have two SMTP servers or two DNS servers, okay? The addresses are known, and you just need to fire a single packet. And there's another one which, to be honest, I didn't try it, but it's something that I use. Let's assume that you have two peering BGP servers, okay? You just fire a single packet. And in many cases, these BGP routers, they drop fragments themselves because of security reasons, okay? Because in principle, they don't need to employ fragmentation. And in practice, I mean, for legitimate traffic, they don't. But if they drop fragments as a security measure, and you are able to trigger the use of fragmentation, then they will drop their own traffic. I mean, this is something that I think that should be tried. I mean, if you are, let's say, you wouldn't try it against systems that you don't control, but it's something to try. And obviously, the implications here is that if you perform a denial of service, of the connection between two BGP peers, I mean, the implications are, way bigger. What is the work that has been done in this area? Well, the first one, we have that document over there, which originally was updating the core IPv6 specification. Same thing. They didn't want to have like a formal update because they wanted V6 to look stable. So what we finally did is in that document over there, just document the problem with these atomic fragments, okay? And explain the reasons for which that functionality is not really desirable. Then, in this other draft here, it's a revision of RFC 6145, which is the specification of translators, like NAT 64, if you want. Translators were the only devices that actually made use of these atomic fragments. Okay, doesn't matter the details, but they were the only devices that were using them. So we are updating RFC 6145 so that translators don't rely on atomic fragments anymore. And finally, the corresponding support has been removed from the revision of 2460 bis. So when that revision of the core IPv6 specification is published, then no specification is required anymore to generate these packets. So you shouldn't see these packets in the real world anymore. Last slide or last couple of slides. Earlier this year, we published RFC 7610. It's called the DHCP version 6 shield, which you could think of router advertisement guard, but for the DHCP version 6, or the IPv6 version of DHCP snooping. Or if you don't know what those two things are about, it's essentially like enforcing the filtering of DHCP packets, but at layer 2. So let's say that you have a switch, okay? And you know that you are connecting your DHCP server on, let's say, the first port. So you want to be able to tell the switch, well, I want to allow DHCP server packets on this port, but not on the other ports, so that no one of the other users of the network can perform DHCP-based attacks. If you have heard or read about Router Advertisement Guard, it's a feature that had been implemented by Cisco that was extremely trivial to circumvent, okay? I don't know if you know if it was fixed? No. No?
I mean, you have to use ACLs with the undetermined transport, then you can...
Yeah, but that's not RA Guard anymore.
Yeah, no, that's not the RA Guard.
Okay. Well, that was, I think Mark, Oise, and myself, we reported that independently to Cisco like 2011.
Yeah, quite some years ago.
4 years. And, you know, we didn't try the same, you know, ideas for DHCP, what Cisco called this DHCP version 6 guard, but I use a different name because RA guard got so much bad press that if we were to publish a new spec with a similar name, it wouldn't make any sense at all. So that's why the name is different. But since we expected them to implement this in the wrong way, we, you know, publish this spec, which essentially tells you exactly how to do the filtering so that the device is not easy to circumvent. Well, the conclusions are, you know, the same that I have, you know, mentioned other times. If you think about V6 and you think about before, it would seem that, you know, we pretty much didn't learn the lesson from before. There are so many of the same problems that were experienced in IPv4 that have been again experienced in V6. There could be other ways to look at the same stuff. Like, for example, the guys working on V4 implementations are different from the guys probably working on V6 implementations. So that's why it's not really that they didn't learn the lesson. It's just different people. And it's also the case that, from my perspective, that if you look at the protocol specifications, they could be doing a better job. Quite a few times, the guy that is implementing a protocol is working on 100 different things. Many of them maybe are not, you know, related to protocols. So the guy just grabs the spec and just, you know, tries to implement whatever is in the document, rather than, you know, do like a security assessment of what's in there. And I think that, you know, if the specifications were tightened up, I mean, things would be a little bit different. Again, I think that there's still stuff to do in V6, while not politically correct. Usually in the IETF, they assume and think that, you know, the protocol is already stable, finalized, and so on. That's not my take. And if you look at the number of updates that have been published and the issues that have been found in the protocols and implementations, it doesn't look that way. But for me, it's just, you know, simply like a data point. It's like, well, okay, there's stuff to be improved, so let's improve it, and that's it. I don't know if there are any questions.
Is there discovery critical, then more secure coming?
We did, actually, we have a couple or at least one or two documents updating it. Obviously, improving some aspects, but there is stuff that is, let's say, impossible to improve. For example, neighbor discovery runs unauthenticated. And what the ITF published something that is called send. Yeah, I mean, it's not going to happen. It would be extremely difficult to deploy. I think there's only a couple of implementations out there. But the funny part was that, for example, when I notified Microsoft, I don't know, Microsoft or Cisco, some of the two, about some issues with neighbor discovery, it was like, well, we don't need to fix that because if you want this to be secure, you have to use send. But that's impossible to use. You don't even implement it. Well, but that's the way to go.
Is there ways of mitigating the attacks or not?
For me, send is to put it in things in a different way. It's like using a PKI for authenticating ARP traffic. For me, it's insane. And actually, there are so many other, I mean, it would be a lot of work, extremely expensive in so many aspects to, let's say, improve the security of something that actually will not buy you much. So that's not where I put my money, to put things in a different way. I mean, painful, yeah. I mean, it's something that it looks good on the, 70-page RFC, but it looks good on the 70-page RFC. I mean,
Well, my outlook is that is putting a different network address global router or prefix or VLAN to port or switch. So you're using 30 network addresses. But if you put a different port for the switch, there's no discovery traffic through the switch. Another router looks like another VLANs. So that's what my outlook looks at it. But it's just a monumental waste of IP addresses, which are using 30 global ones rather than all the routing IDs.
Yeah, with some of the, the neighbor discovery and the attacks that, we discussed that in courses and so on. My take is that if you are really, in those cases in which you are really concerned about them, you just segment the network. If you are really concerned about that. And also there are so many, like for example, let's say that you have, you have authenticated, neighbor discovery. But if still the DNS, is not authenticated, it's like, what's the point, for example? I mean, there are so many pieces in the puzzle that doesn't make any sense at all, that like putting a lot of money and effort on improving something that at the end of the day doesn't buy you much. I don't think it makes sense. And even then, far as I recall, if you look at, Linux, Windows, and maybe a few others, they don't implement send at all. So even if you want it, impossible. So if you have any further questions, feel free to send me an email. I'll be during the week, during the whole week here. So it's just, when you see me somewhere, particularly if it's before the party on Wednesday. And also, if you're not subscribed, there's the IPv6 hackers mailing list. It's a mailing list. We have like more than 1,000 subscribers, and it's a low traffic mailing list. So it's lots of people read what you write, but at the same time, you don't get like, nonsensical messages all the time. So thank you.